Thank you very much for inviting me. It's always a pleasure to talk about advanced air mobility. I've been involved in making distributed electric propulsion airplanes and now these operations a reality, and working very closely with the FAA. We have probably about 40 different lines of business across air cert, flight standards, and ATO, the Airspace Operations Group, that we meet with weekly. We go over these safety scenarios that we're going to conduct, understanding contingencies, and try to cross-pollinate the FAA to kind of get out of the stovepipes of what they normally focus on day to day and think about kind of other lines of business in the FAA and how that affects really what they do for their piece of it. So just a quick update on where we are right now. So we are currently in the phase of the project which we call this developmental testing phase. Here's my timeline. And what we wanted to do there was first understand the readiness level of industry, so both on the vehicle side and the airspace service providers. So we got contracts in place with Joby Aviation and about 11 different airspace service providers. We also needed to build up a way to connect the vehicle and the airspace in a cloud-based environment, and we've made it so that all of our capabilities are mobile. So we have a mobile operating facility that has all the necessary surveillance and kind of control center, and it's connected to our NASA Ames cloud environment that has emulations of the airspace. You can visually see what the airspace service providers are visually doing. You can kind of see that in the center picture. So you have the situational awareness of the whole operation from point A to point B. And you can see, how the airspace service providers are submitting flight plans and communicating with one another. So those things are being built up. We just the helicopter, this little cartoon helicopter, just showed up today out at NASA Armstrong. It's a OH-58 is what we're using, and we basically built a blueprint, I would call it. So we're trying to anchor to the current FAA standards and build a flight test plan to understand how the performance in the terminal operations compares to helicopters, because that's the kind of regulations and flight test techniques that we have right now. So we'll be looking at handling qualities and like rotorcraft dynamics. And this will just become like a blueprint of here's the kind of tests that we want to conduct with an eVTOL, and understanding how you would even translate some of these handling qualities, test methodologies to, from a rotorcraft to a distributed electric propulsion vehicle. And so those are the kinds of, what we call, we're anchoring and evolving. So as we identify what some of those changes look like. And in a lot of cases, the distributed electric propulsion is going to look better from a performance standpoint than a rotorcraft. But still, we have to put in, some sort of, standard that, well, this is what we think, the lowest performing capability needs to look like to maintain the level of safety that we currently have in the NAS. So we have a week of flights this week. We'll come back first couple weeks of February, get some more flights. We'll bring in the airspace service to function while we're flying, and then we'll have some final March flights to test out, kind of do an end-to-end test of our system of systems, and then we'll go test with Joby Aviation. So this is a breakdown of all the components that speak to each other during one of our operations. And what we're trying to do is we have an announcement of opportunity that comes out at the end of January. And that's where you basically want to take every one of these icons and replace it with industry capabilities. So right now, NASA's built a capability that we can conduct the entire operation, and every one of these pictures can be provided by NASA as a whole. It's just like whatever today's state of the art is. But as we partner, we want to look at what the scalable solutions are going to look like that industry is proposing for each one of these pieces of the puzzle. So we also, one of the things I didn't mention is we also have our partnered national campaign is partnered with the Revolutionary Vertical Lift Technology Project at NASA, and they have an acoustics research area where they're studying what the signatures of distributed electric propulsion looks like in the many different configurations that we've been seeing them. So that's another piece of the national campaign. And there's going to be different area surveillance and weather solutions. We have some that we start with now. Another missing link that we're going to build the capability first and then see what solutions industry might have is there's got to be something in the cockpit. These first vehicles to be certified are going to be piloted. So there's got to be something that talks to the pilot in the cockpit that comes from the airspace service provider, not just of putting in a flight plan, but really the main thing we're focused on is all the contingencies that can happen. So a contingency could either initiate from the vehicle, like maybe they have a degraded mode. The winds were too much as they were trying to do an approach and they have to go around, but you have now a bunch of other eVTOLs that are stacked behind it with their own estimated times of arrival, and that disrupts the whole traffic flow. You could have an airspace service provider that's monitoring the health of the vertiport, and there's something has gone wrong at the vertiport such that the vehicle coming in can't land there, and they have to do a go around. Well, when you start thinking about all these different contingencies that can happen in that terminal operation, that's a lot of energy for these eVTOLs. And so the other thing we're trying to think about is, well, what should the reserves look like for these vehicles? Because right now there's 30 minutes reserves required, and that's a lot of weight to carry on the eVTOL. But before you could come up with maybe a different solution than needing 30 minutes, you have to understand the operation. Is it, a 12-mile, 15-mile route, and where, emergency landing spots are, and how much energy does it take if it takes you a couple times to land, or you got to loiter for somebody else who's had a landing problem. And so what does that energy management look like for those contingencies, and how's that fit in the reserves posture? So those are things we're looking at. This next chart just shows our first scenario is just the basic no anomalies happen. We're just flying from point A to point B, and we submit a flight plan, and we show that we can maintain the time of arrival that was predicted for us in whatever environmental conditions. So you might have higher density altitude, you might have winds and that sort of thing. So just basic vehicle performance. And then we'll start studying everything else, whether you see there's the noise evaluation. So that, again, that's a very specialized test of how you create a acoustic array for these types of vehicles is the first kind of step that we have to figure out. And then, there's specific flights and speeds and altitudes you have to fly above that array to get the information that you need. But then we'll look at the communication, navigation, surveillance contingency. So we have GPS denied scenarios. What are the company's solutions to be able to navigate their vehicle without GPS? We'll have the interoperability. So I already talked about the things that happen in the terminal operations contingencies. There'll be air-to-air conflict management up and away, but what's even harder to assess is the terminal operations area of how we're going to do detect and avoid, like well clear or collision avoidance. So what do some of those sensors and autonomy look like on the vehicle? And then there'll be a constrained conflict management. What we mean by that is typically when a contingency happens, there's a domino effect of other contingencies that end up becoming something new that you didn't plan. So if let's just say I have to do some go around and I have a degraded vehicle, but I have these airspace constraints that I'm having to stay within. So the direction I need to turn to stay out of my my airspace constraints, I turn into a direction that there's other traffic that could possibly be a collision. So now I have to figure out, like, okay, I gotta miss this collision. That's a higher priority than worrying about staying in my airspace. And then, it could be another maneuver you make, ends up taking you towards a tower or, some terrain or something like that. So we have to understand how the automation, the outer loop automation on these vehicles for navigation can also solve what the most stressing contingency is at that time. So that definitely is each of these are trying to really assess how do we certify that software for the automation, that it is the first front of dealing with contingencies, and not the automation is there, but the pilot is the ultimate one in control. So we need to make the software assured enough that it's predictable and it can make the right decisions for the pilot in these emergency situations. So back to our timeline. So I mentioned we have the collaboration announcement coming out, and that will be for NC1 partners. We'll onboard them and start planning around, where they're going to be flying, a range or an airport, get these specific UAM routes that we've developed that are performance-based routes. So, we're going to have some kind of a loiter pattern, but it has to be, something much smaller than setting up in a fixed wing pattern. And there's got to be, places where you come out of that loiter that is, best for maybe the crosswinds of the day. In these urban environments, you're not going to have a lot of flexibility to be able to land into the wind because you'll have constrained structures around you in a very specific route that you need to take to enter into that heliport. And then you also think about, there's going to be a lot of obstructions in an urban environment. So we're looking at steeper approaches and less time for those steeper approaches. So the vehicles want to stay, the ones that are wing-borne want to stay on the wing as long as possible and be in a vertical state the least amount possible. So we'll have more partners than developmental testing. On purpose, developmental testing we were trying to keep that kind of small, just to verify scenarios and the capabilities that NASA needed to develop. When we get to NC1, now we start getting out at the airports and understanding how these helipads and vertiports that are going to be leveraging airport infrastructure are going to coordinate their routes and deconflict with existing traffic at the airports. And of course, we'll look at the contingencies. Everything will be very scripted, so it's not like we're going to surprise somebody with the contingency, but we're really just trying to understand the performance and timing around having multiple vehicles, flying different routes, and what's the spacing between them need to be, how much time do they spend on the ground, and how much time do they need to charge, those sorts of things. So at the same time when we do this announcement for collaboration at the end of January, we're also bringing on partners that wouldn't be ready for NC1, but they'd be ready for NC2. And that's where NC2 is where we're really focusing on more levels of automation on the vehicles. And because, you have a lot of companies that are trying to figure out just right now how to fly a safe electric vehicle. We're trying to get a head start at NASA of working some of those automated pieces to help industry keep pace a little bit faster with this timeline that we have. So we have some NASA research projects doing some automation work, looking at the software assurance methods, what's certifiable, and then hopefully, we'll do some. The blue line means, and the blue box means that NASA is going to fly their own automation research on our own vehicles to make sure they're safe, and then we can hand over with our partners some of that work for them to fly on their vehicles in the national campaign, the second national campaign. So each series of the national campaign creates a more complex operational environment, which is going to need more automation, not just from the vehicle, but from the airspace service provider, where you're going to really need two machines that are negotiating, volumes of space, deconflicting with each other, times of arrival, times of departure, and then the contingencies that are going to happen, and then giving everybody in that operation situational awareness to any of those contingencies, how it's going to affect them. And some of those contingencies, you are going to have to bring ATC into the conversation. So it's not just this, PSU to PSU communication. There has to be other safety nets. If you're, if you realize that you're going to intersect some existing traffic that ATC is managing, then you have to go direct to ATC. So it's trying to figure out how and what that looks like, from a ATC standpoint yet, right, it's still in formulation. So like I mentioned, our motto on the project is anchor and evolve. And so like I said, we have a flight test plan that takes these standard flight test techniques for rotorcraft and the terminal operations, and we'll get some baseline data with an OH-58, and then as we start to fly with the eVTOLs, figure out what's the required and desired performance metrics that we need to instill into these vehicles. So right now, this is a little picture out at NASA Armstrong Flight Research Center, and we have put in multiple helipads. So we got a helipad here, and there's a so we call this a vertiport. So it is still, we follow the heliport circular. So all the obstacle avoidance, the terminal procedures and everything is by the book. But what we put in between these two helipads is basically like two short runways. But you could also refer to it as an extended FADO. And so this is to evaluate vehicles that in degraded modes are going to need some forward momentum before they can touch down. And there's some vehicles out there that are just looking at short takeoff and landing configurations. It saves a lot on their energy consumption. It doesn't take a lot of real estate for them to land and take off. And so the value proposition of the money that they can make per passenger and carry more weight and less battery, a lot of them see a great business case there. We'll also look at helipads on either side of a large building so that we can understand approaches and departures from a windward heliport versus a leeward heliport next to a building. And again, we've come up with approaches that take into consideration what G's that the vehicle is, or the passengers are feeling in the vehicle as they come in and arrest their descent and come into land. And trying to do all of this, so keeping passenger comfort in mind, but also the performance of the battery. And then of course, understanding what degraded modes look like for these vehicles. So the ones that are wing-borne, in the FAA standards, you always have to be able to show how, when you lose all power, you're going to land a vehicle. And I know all the companies say, well, we have all these redundancies in the system, but you have redundancy in twin engine airplanes, and pilots forget to put gas in it, or they forget how much gas they had and they run out of gas. So if it will happen. There'll be a full power outage. And so what is that contingency to get down? So for the wing-borne vehicles, they have enough wing to have a glide slope. So that could be their contingency. If you have something that's more of the octocopter kind of thing, and you had a full power loss, then maybe they're going to have to. They don't have an auto rotate, so they're going to have a parachute maybe or something. But that's one of the things that the FAA has to think about. Like, do we really have to consider a full power loss? Can we prove that there's it's impossible with the level of triple redundancy that you're going to get in a mode where you literally lose all power? So those are other things that we need to evaluate. And this picture on the right here just shows the hard deck that you set up that protects the vehicle from all the obstacles underneath it. So we've literally laid out we have placarded actual airports. When you see OH01H, that's an airport, a registered airport. This is a registered airport. This is a registered airport, and even these runways are a registered airport. So, going through the paperwork of the FAA, what they expect to see in building up these new airports, right? That don't have existing placards. So we're thinking with an eye towards IFR flights. We want to be able, these vehicles need to be able to come in and do auto lands. If you're going to get the timing and the spacing between them much narrow. And so right now there aren't IFR approaches down to the ground for helicopters, but that's what we're going to be evaluating, what's needed to do that. And then we have the second landing site that's about 18 miles from, this is the main campus at NASA Armstrong, and there's another place out in the desert where we have another helipad, so we can get some routes and have contingencies happening in the route, or after you've spent some energy and now you have a contingency at the other end. So here are some of the evolution that we're trying to understand. So how do power relationship in helicopters compare to eVTOLs? Where do existing performance requirements for engines need to evolve for the electric VTOLs? How sensitive is e-power to atmospheric conditions? What it means prior to takeoff to determine propulsion system is capable of delivering the power required to achieve the published performance. So when we say published performance, that you go into any of these airports and it's going to say your vehicle has to be able to do these things to get into this airport or this helipad. And so you're obviously, when you submit a flight plan, you're going to have to say, this is my vehicle's capabilities. And, the aerospace service provider is going to say, well, these are the only helipads that you have options to go into because there's too many obstacles or crosswind higher crosswind needs at some of these helipads that your vehicle can't do. So just understanding how we placard those helipads or that infrastructure. How does fuel efficiency variation with speed, altitude, and gross weight compare between helicopter and eVTOL? What evolutions in flight test techniques will be required for eVTOL certification? How do we automate dynamic rerouting between the pilot and the operator of an airspace service provider? And as UAM scales, how will we manage spatial data integrity? So if we're trying to automate a lot of the operation, that means that just the three-dimensional space, so that spatial integrity, and the vehicle's ability to track it very accurately, and the airspace service provider being able to have a surveillance system that is very accurate is the only way we're going to get to these automated, closely spaced with auto land capabilities. So even that, I mean, we're already starting to show, in some of the FAA tools, there's mismatches between spatial data answers for different tools that they have for surveillance. So I will, I'm trying to give everybody some time to ask questions, so I'll stop there, and you can let me know if there's some questions.
Yes. Thank you for the very impressive presentation, and thank you again for sharing what is happening in NASA. And we got 3 questions so far. So the first one is, what kind of metrics and flight conditions do you consider for noise evaluation? Noise evaluation. Yeah.
For noise evaluation, what kind of metrics?
Oh yes, what kind of metric and flight conditions are you considering?
Yeah, so I mean the way that acoustic arrays are developed is based on how far the noise propagates, and so we would have arrays that could be as much as like 2,000 feet wide by 4,000 feet long. And they have to have it has to be a very flat area. Otherwise the noise will bounce off of structures or even hills. So we're taking some of those fundamentals in helicopter testing, and then trying to evaluate how does that array size change with these vehicles that are claiming that they're much quieter, 10 dB quieter than helicopters. And what's the signal to noise ratio? And then I saw, hey, hi Ian, just popped up.
I was just going to jump in because the actual metrics you guys are going to be looking at are A-weighted dB and EPNL dB. And there's some pretty standard approach and departure procedures that you can look at to measure.
So let's see. So does NASA include cargo delivery service? Yes, but we have right now we put in our announcement, you have to have a minimum of 300-pound payload. But yeah, we will be doing remote pilot operations. We just put an announcement out that we just partnered with Whisk. They're passenger carrying, but they could also be cargo carrying if they wanted to. So yeah, that's a fully autonomous capability that they're looking at for their business case, which means it's going to take them quite a bit longer, obviously, to find a certification path. Looks like most of the activities you're planning to do is related to safety and automation. Is there NC scenarios or plans for evaluating costs and efficiency of dense operations in the future? Turnaround time estimations. Yeah, I mean, we have our NASA Langley group that does vehicle systems studies. They'll, as we kind of produce numbers of how the timing between these contingencies, the capabilities on the vehicles to navigate precisely, we can feed that into models that they've been assessing for these business cases all along. Yeah, so then we have the noise scenario. We'll just be doing that one at a time. For us, doing the noise assessment is for NASA to understand if their tools that they use to predict noise are accurate for distributed electric propulsion, and having multiple rotor blades at different angles from horizontal to vertical. So what do those effects look like with flowing over the wing and interacting with each other? So those tests are for one vehicle at a time, so that they can make sure that they can validate their tools can make the right predictions. And does FAA develop air traffic and fleet control system for UAM private sector? Well, we're working with the FAA. We're developing UAM routes, so they'll be like their own corridors. That's not interfering with existing traffic. So we'll do that all under the auspice of the FAA rules. But what we'll have to do is what we're asking them to do is not be in contact with ATC during nominal operations. So that you have to get a letter of agreement to work with them to do that, and then in that letter of agreement you'll say, well, these are the times that we will talk to ATC. And this is the equipment we'll have in the vehicle. And that sort of thing. But that's just like in today's rules. And so obviously what we're trying to understand is how we're going to scale that, and how is that going to change FAA regulations. Okay, I think I'm out of time, right?
Oh, yes. Thank you for the
Okay.
answers. Yeah.